compromise of these two. And one thing I also want to remind you is that, okay, you know, for all these figures, you can see we have the prior, we have likelihood, we have the posterior. But prior and the posterior are distribution. They are probability distribution. In other words, their integral is 1. But you can see that we actually indicate that this is HCI, but you know, don't worry about that. I mean, you can see we only mark these two, right? The HCI for these two, but not this, not the likelihood. Why? Because likelihood, you know, likelihood is not a distribution. Because, I mean, you say, hey, wait. I mean, previously we say like a binomial distribution. I say it's a distribution, right? So how come you say binomial distribution is not a distribution? Remember, when I say binomial distribution is a distribution if the x-axis is what? If x-axis represent the number of flips, the number of heads, right? If the x-axis represents number of heads, then it's a distribution. But the binomial distribution, if now the x-axis is not a head, it's theta, right? It's theta. So if you consider the function of binomial distribution, and then you use theta to draw the x-axis, then it's not a distribution, okay? Even though it looks somewhat like a distribution, but it's not. In other words, the integral not necessarily will be 1. It's not necessarily 1. Okay? For the likelihood. That's why we call it likelihood. We don't call it likelihood distribution. It's just a likelihood. Okay? Be very careful here. So, well, that's the end of this example. Any questions so far? We still have 10 minutes. I think I'll probably will have just enough time to talk about the definition of the beta distribution. Okay, as you can see that, okay, yeah, I mean you can see that for the prior here, we still use the discrete prior, right? I just try to, you know, have so many points, divide like you know, the range between 0 and 1 into so many points, so that it looks like a continuous, but really, I mean, for this, you know, 4 cases, we really the case we really consider are discrete, okay, are discrete, but well, I mean, when you consider prior, I mean, because shouldn't we consider like a continuous case? Okay, but once it comes to the continuous case, then, well, it's going to involve like a integral, as I said. I mean, the integral is the difficult, right? It's difficult, but we could consider a certain prior that makes our case easier. That's the conjugate. Okay, the conjugate. Okay, and for the conjugate, okay, prior, okay, it depends on the probability. On the likelihood. For different likelihood, you have different conjugate prior. Okay, for binomial distribution, I should say binomial likelihood. The conjugate is the beta distribution. Okay, so what is beta distribution? Okay, so beta distribution is defined like this. Okay, it's a very common distribution in Bayesian statistics, and it looks as follows. Okay, P of theta equal to, you know, this thing called gamma, okay, gamma function, gamma alpha times gamma beta, okay, as denominator, and on the top is gamma alpha plus beta times theta alpha minus 1, 1 minus theta beta minus 1. Okay, so it's a little bit complicated, but you will see that this beta distribution has a very good property later. Probably not today, because today, I mean, we only have like less than 10 minutes left. So I can only introduce this beta, this gamma distribution. Sorry, the beta distribution, okay, which is based on the gamma function, okay. So if you look carefully, okay, you can see beta distribution looks similar to binomial, okay, because, well, you can see the binomial, we have a combinatorial number in front of it, and then we have theta to the power of something, and 1 minus theta to the power of something. In terms of shape, it looks similar, right? I'm not saying they are the same, but in terms of shape, they look similar, okay? So, okay, except for the first term, the one with all those gamma, okay? The first term is a normalizing constant, okay? This one is a normalizing constant. Gamma alpha times gamma beta, this is normalizing constant, okay? That ensures the distribution integrates to 1, okay? And gamma represents gamma function. We can see from the preceding formula that the beta distribution has 2 parameters, alpha and beta, obviously, okay? So here, just want to give you an idea, okay, what beta distribution looks like, okay? So we have, well, 1, 2, we have 4 columns, 4 rows, okay? And, you know, with different alpha and beta values, okay? So you can see for the same row, okay, we have the same alpha value, but with different beta value. The beta value increase, okay, from left to right. For the same column, we have same beta value, but with different alpha value. And again, alpha value increase from the top to the bottom. Okay, so you can see that, okay, when alpha and you know, when alpha is you know, higher than beta, okay, or put it in our way, alpha increase, okay. For example, like here, okay, alpha, say we take this one, okay, you can see alpha equal to 0.5, beta equal to 2.0. When, you know, beta stay the same, but alpha increases, you can see that the height, the center, or the height of the curve moving toward to a right, right? Moving toward to a right. But when beta increase, alpha stays the same. Okay, for example, like here. The max of the curve moving to the left, right? So that's first thing you need to remember. Alpha help the max moving to the right. Beta value help, help the max moving to the left. But if alpha and beta value both increases, what happens? You can see this diagonal. When alpha and beta both increases, you know, they are more and more concentrated at the center, right? So because it has these 2 parameters, it is very flexible distribution. we can use it to model stuff very easily. Okay, you can see that even include when alpha and beta are both 1, we can even include this, this is pretty much like a uniform distribution, right? So uniform distribution is a special case of the beta distribution. Okay, so beta distribution is very versatile. That's the first thing, we know, which is good. Okay, so I think I already, so as alpha and the beta, okay, they are put A, B, but you get the idea. Gets bigger together, the beta distribution gets narrower. Okay, the values alpha and beta are called shape parameters of the beta distribution because they determine its shape. Okay, so alpha beta are called shape distribution parameters. Shape parameter. The shape parameters can have any positive real value. They cannot be negative. Okay, in beta distribution, alpha and beta, some textbooks say A and B, but you get the idea. Okay, so they can only be positive real number. Okay, and we can use the beta distribution for the prior of theta. Okay, because first, beta distribution is restricted to be between 0 and 1, which is in the same way our theta parameter is. Remember, when we throw the coin, the probability that the theta represents the probability that the coin flip is head, right? So that it can only be, the value of theta can only be in between 0 to 1, right? And which is like also the same case as beta distribution. Okay, because you can see here, okay, we only draw, this curve, okay, between 0 and 1. Okay, second, okay, its versatility, okay, as I say, like it has many different shapes. Okay, so distribution adopts several shapes, all restricted to 0 and 1, of course. Okay, so which include uniform distribution and the Gaussian-like distribution and the U-like distribution. U-like is like here, okay, obviously the upper left corner, and the Gaussian distribution is like Gaussian-like distribution. It is not really Gaussian, but it's similar to Gaussian, which is like this, right? This looks like bell shape, right? So it's very versatile. You can sort of include like all type of shapes. You can consider all type of shapes if you use beta distribution. The third one is beta distribution is the conjugate prior of the binomial distribution. What is conjugate prior? It means like we can solve this the integral. Okay, mathematically solve the integral, which was not possible in many other priors. Okay, so this is like the third reason. Actually, the third one is the most important reason. Okay, but for that, I think we don't have time to talk about that today. Okay, so probably we stop here. Okay, next time we start from here, the conjugate prior. Okay. So any question? And remember, okay, that the questionnaire, okay, I will post that as like a bonus for homework 1, and it will accounts for 20 points. At the end of the questionnaire collection, I will get the names, who fill out the questionnaire, and and add 20 points to your homework 1, basically. Okay, of course, I will post it in the E class for you guys. Okay, so please remember to do it.